ground and gamma bands in collective spectra. This is based on the irreducible representations of the group SU3, which form the so-called SU3 multiplets. Then I will show how it can be connected to the proxy-SU3 model. The idea is that the vector boson model defines the spectra through the given quantum numbers which characterize the SU3 multiplets. But these quantum numbers are not fixed in the model for any physical reasons, while this is done in the proxy-SU3 scheme. So the idea is that we use the Hamiltonian formalism of vector boson model and apply the irreducible representations of SU3, which are obtained in the proxy scheme. Then I will show some very preliminary calculations with these irreducible representations, and we'll conclude about how this can be useful in the future. The vector boson model is based on the idea that some collective excitations in atomic nuclei can be described by two types of elementary excitations created by two operators, which have the differential form of bosons and vector bosons with three different components. They can be presented as such differential operators with such properties, and their commutation relations are bosonic ones. With these operators, one can construct the angular momentum operators and also the quadrupole momentum operators. And all this system of operators close the algebra of SU3. So this is very well known and used property of these operators in several model applications, including interacting boson models, symplectic models, and others over the years. But this realization of this with these so-called vector bosons is a bit specific, because it provides some special properties of the operators, which are then used to construct other operators and determine the physical properties. They have no direct physical meaning as particles or a couple of particles. They can be thought as a kind of phonons, but still they cannot be related to specific motion or particle structure. They are simply related to collective excitations. Then for SU3, it's known that it's usually embedded in a higher UN unitary group, and in this, when this group is reduced to SU3, there appear SU3 multiplets, SU3 irreducible representations, which can form some multiplets, and they are characterized in nuclear physics classically with these two quantum numbers lambda and mu, which are obtained by some subtraction of Young diagrams in the U3 representation. But this is too much mathematics for the moment. The important things which are needed for us for the physical problem is to know that there are some invariants with respect to the SU3 group with which one can construct different structures. So the simplest invariants are the second order Casimir operator and cubic Casimir operator. The second order Casimir operator is related with the quadrupole operators and the angular momentum operator in this way. And they have some eigenvalues in the matrix representation of SU3, the basis of the matrix representation. Then this is the dimension of the representation, and what is important in this approach is that the two vector bosons transform as O3 as O3 independent with respect to two independent O3 irreducible representations with this form, lambda mu 1, 0. Then one can use these structures to create appropriate model Hamiltonian. There are three operators which are invariant with respect to O3, and some of them reduce SU3 to O3. This reduction is important because in this way, having these operators included in the Hamiltonian, one can generate the spectrum. This is due to the fact that these operators, including angular momentum and quadrupole momentum, and these two operators which are directly created by vector bosons, this couple of operators has the meaning of alpha type structure, quartetting structure of bosons. So these operators reduce SU3 in a way that there is some degeneracy and breaking of the symmetry in which the different bands with angular momentum are created. So different rotational bands are created in this reduction. There is appropriate basis which can be constructed with respect to this reduction chain, the so-called basis of Bargman and Mushinsky. And it's characterized for given irreducible representation of SU3 by the quantum numbers lambda and mu, angular momentum and its projection, and another quantum number which determines the multiplicity of the appearance of the O3 representation in SU3. This, in simple words, this means that how many times a given angular momentum appears in given irreducible representation of SU3. And this means how many different rotational bands appear in the spectrum. This is the important thing here. The Hamiltonian is not diagonal in the basis, and then one has to diagonalize it. It's possible to do this almost analytically because the matrix of the Hamiltonian is tridiagonal, and in this paper it was elaborated method to do this. In this way, the physical states are represented by the basis states with these coefficients which are determined. Then there is some rule according to which one can determine the quantum number lambda of multiplicity for a given L. And what is important here is that having quantum numbers lambda and mu and alpha, one can obtain a quantum number which is analogical to the third projection of the collective angular momentum on the rotation axis, and this is the number of vector bosons. Then the structure of the spectrum is determined by different values of the quantum number alpha. The maximal one determines the ground state band. Next smaller one determines the gamma band, and then other values of alpha until reaching 0 determine band built on 4 plus state and so on to state which is with band head k. And k is determined in this way. So one can also calculate any transition rates between the states of the bands which appear in this SU3 representation, so-called SU3 multiplet, intraband and interband transitions. So here are constructed different ratios between them, so to avoid using effective charge. So one having this formalism can consider different possible structures of the spectra. And the structures of the spectra are determined by the quantum numbers lambda and mu. Especially mu is important to determine how many bands appear. So I give here some simple example. When mu is 2, we have only 2 bands, ground and gamma. When mu is 4, appears 1 4 plus band. Then when mu is 6, 1 more band, and so on and so on. In practice, what is useful from this model, this is the ground and gamma band, because the other bands, there are examples where such bands exist, but there are not too many. So whatever the irreducible representation is, we use the model to determine the ground and the gamma band. But the structure of the gamma and the ground band depends on the presence of the other bands even if they don't exist. So it can be depend virtually, so that the different lambda mu representations are important, and they provide different structure of the spectrum which is of our interest. What was done many years ago was that since we have no, in this model, physical reasons to determine which should be lambda mu and that subsequent to the spectrum, we used to make some kind of net over lambda mu to check what is the description which they provide for the gamma and the ground band. Here is given the root mean square deviation for the description of both bands. They are described together with the transition rates, but here I give only the RMS factor. And it's seen that in some part of nuclei, in rare earths, there is some minimum for given values of lambda and mu. And it appears that this minimum is at mu equal to 2. And for other bands, for other nuclei, it appears that with increasing lambda, all values of all RMS values go to some saturation, and there is no determined minimum with respect to lambda and mu. It appears that in the first case, the splitting between the ground and the gamma band, so the displacement of the levels with the same angular momentum, is smaller, and in this case it's larger. And such a behavior of the interband spacing is characteristic for the nuclei towards the second part of the shell. So this is an interesting observation, and I will show you how this then relates to the proxy-SU tree. Here in this table, we collected these RMS factors, and it's seen how they are correlated with the splitting of the multiplet. This is the difference between the two plus states of the gamma and the ground band, normalized on the first excited state of the ground band. Then we see that here for lighter rare earth nuclei, we have this minima determined in some lambda mu multiplets. While here we can only say that the lambda should be larger by some value, some larger value, to get saturation to some lower RMS factor. Here we give mu to be 2, but it appears that also a larger mu give almost the same RMS factors. Then we decided to see how this situation develops in case if we fix the SU3 multiplets by the proxy-SU3 model. The proxy-SU3 model, it will be presented in more detail by Dennis, so I will not go in this. But the idea is there that you make some mapping of the band of the single particle structure. You take, you replace the intruder orbitals which enter given shell with the orbitals which are pushed from the same shell, which are pushed down, and then you consider a new type of shell structure which is characterized with SU3 symmetry, which is otherwise destroyed by the spin orbital interaction. Having this new shell structure, you have also a new way of appearance of valence particles, and on the basis of these valence particles in these proxy-SU3 shells, one can determine the SU3 multiplets. This was done for the rare earth nuclei, and here I show how look the lambda mu multiplets, lambda mu irreducible representations for the nuclei which I showed in the table before. You see that in most cases mu is large number, and this number means that there are other virtually appearing bands which influence the structure of the ground and the gamma band. This is also the results. These are results obtained in the actinides, and this is uranium-238, which I showed in the table, and for which we see that here this value of lambda and mu is obtained. So very large lambda and small mu, which is, by the way, very similar to the behavior of the SU3 multiplets obtained in the empirical study in the original SU3 boson model. So what we did, these irreducible representations determined in the proxy-SU3 model were taken, and calculations were made in the vector boson model. Here in this table, in the first line, I give the original vector boson model calculations with the lambda mu multiplets obtained by adjusting to experimental spectra, blue. In red, I give the result in case of using SU3 multiplets from the proxy scheme. We see that here are the RMS factors. We see that for the nuclei where some minimum was observed in mu equal to 2, these are the nuclei with small multiplet splitting. The proxy-SU3 symmetry gives some deviation from the best RMS factor, but it's not crucial one. So we can only say that using physically motivated values of the lambda mu, we give some deviation with the best cases, but still they're in physically reasonable range. What is more interesting is that when you go up with the masses here, we observe that in the cases where there is no observed minimum, but we determine some areas where lambda and mu should be, the results appear to be very close to one another. For example, you see here and here in this heavier nuclei. So both the so-called favored SU3 multiplets obtained in the vector boson model and physically motivated SU3 multiplets obtained in the proxy-SU3 scheme provide the same model description, which means that in this region we can simply say that we have an SU3 scheme in which the Hamiltonian is determined by the vector boson structures, while the multiplets are physically determined by the proxy-SU3 scheme, and it seems that this is a range in which we have a closing, a full SU3 symmetry description of the ground and the gamma band. So this result is very preliminary. Of course, one should check how this works in other nuclei, to what extent this is correlated also with the transition rates, and what is, after all, the meaning of this change of the situation from the small multiplet splitting to the larger splitting of the multiplets. There are some ideas which can be developed, but this needs some time. To conclude, I can say that from one side, the vector boson model algorithm appears to be applicable with the use of proxy-SU3 defined multiplets. This is well shown now. On the other side, in turn, the proxy-SU3 symmetry obtains further physical significance in the structure of nuclear collective excited spectra, especially for the ground and gamma bands. And this shows that we can speak about vector boson model with broken proxy-SU3 symmetry, and this can be applied further to make further analysis to consider wider ranges of heavy, even deformed nuclei, and then eventually make wider applications, also helping to experimentalists to interpret their data. Thank you for the attention.
Thank you, Nicolay, for this very informative talk. Are there some comments, questions on this talk? maybe I have some remark or something. If you could go one transparency back where you had the numerical result, well, you had the numerical results. Yeah, that's right. It seems clear. It seems clear. It seems here that the results get better in the upper half of the cell, of the proton cell. Erbium is in the middle of the proton cell. So after that, the agreement gets much better. Maybe one reason could be the influence of the pairing force. If you have very few collective proton-neutron pairs like it happens in the beginning of the cell, then the influence of the pairing will be higher. If you go beyond the middle of the cell, you have many proton-neutron pairs creating collectivity, and then the influence of the pairing will be much less. So maybe this kind of
blocking effect. This is the blocking effect when you have power.
Yeah, that's right. So it is reasonable that as you go down the list, you get improved the results, I guess.
Yeah, we should think about all these details.
Okay, one has to work more detail, sure. Are there some other comments or questions? If not, let us thank the speaker again.
There was a question.
Oh, there is a question. Yes, please.
Which potential use in your work in time?
The potential is practically determined by the Hamiltonian. This is not potential of the type of Bohr-Mottelson potential. It's an algebraic structure, which is, however, to some extent equivalent to the potential which Bohr and Mottelson determine, or any other potentials. And there are some works which show what is the equivalence between this. For example, this is done in the interacting boson model. Not here, but here can also be done. In all cases, this is potential which is close to something which generates rotation. It should be deformed potential.
Yes.
So, how do you define the parameters there? I can see It's okay.
They are adjustable parameters. These are the only three parameters which are adjusted to ground and gamma band energy spectra and all transition rates which are available.
But do you mean that you take experimental data from nuclei that we know and then you go beyond? I mean, how do you find it? Do you do it for each nucleus? Or
Yeah, this is done for each nucleus.
Okay.
It could be thought about making a common set of parameters. We didn't do this for the moment.
And where is your pairing?
There is no included pairing in the usual way. This is collective model. This
Okay,
is
so
algebraic model. And the pairing is not included. It's maybe implicitly somehow enters, as Dennis says, that the model feels how the pairing behaves, but there is no pairing directly.
Implicitly. Okay.
Yeah.
Okay. Thank you.
I guess there are no other comments, so let us thank our speaker again. Let me invite our next speaker, who is Professor Angela Gargano from Napoli, Italy, and her subject is nuclear structure studies with a realistic cell model framework.
Good morning to everyone. Let me open the... Here? Next, right, this one. Okay, perfect. So, again, good morning to everyone. It is a pleasure for me to be here. It's the first time I participate in this conference, and I would thank for this all the organizer, in particular Professor Atina Pakov. It is also for me an opportunity to visit this beautiful area. I ever knew before. So the title of my talk, as the chairman said, is a nuclear structure studies within the realistic shell model framework. However, due to the limited time, I'll focus in this talk on a specific aspect, namely the role of three body forces within the shell model framework. And in particular, I'll report some results of our recent review paper. The reference is here. It is well known that three-body force, the role of three-body forces is well assessed in light nuclei, and exact calculation have been performed for system up to mass 12, and here I have reported a picture from this review paper by Carlson, where I have compared experimental spectra from helium-4 to calcium-12. Experimental spectra are compared with results obtained with the nucleon-nucleon interaction argon V18 and the interaction including the Illinois three-body force. As you may see, the contribution of the three-body forces is essential to reproduce, to give a better agreement with experimental data. This is more clear here, where I have reported some no-core shell model calculation, in particular for barium-12 and carbon-33. Here we have the argon V8 and different forces, including the three-body components. As you may see, all considered three-body forces give similar results, but they are dramatically different compared to the calculation with only the nucleon-nucleon potential. In particular, the inclusion of the three-body force is essentially to give the correct ground state in barium-10 and the correct splitting of the 1/2 and 3/2 levels in carbon-13. But the focus of this talk is on the role of shell model of three-body forces within the shell model. So just a slide on the framework we use. You know, the shell model, in the shell model, we only consider, clearly the shell model is based on the mean field ansatz that allow us to define a potential, and so three different spaces, a core space, a model space, and external space. And in the model space, we only, in the shell model, we only consider explicitly the valence nucleons which are constrained to move in a limited space that is in fact the model space. So the shell model Hamiltonian is composed by a one-body term and the two-body terms, and this Hamiltonian acts only between the valence nucleons, and it is defined in the model space. So we have to construct this Hamiltonian, and because clearly this Hamiltonian should take into account for the degrees of freedom we have not considered explicitly in our calculation. Usually a large number of shell model calculations are based on phenomenological interaction. However, we can construct microscopic interaction, namely we can start from the bare nuclear potential, use many-body theory, and derive an effective interaction. However, it is well known that when we start only from a nucleon-nucleon interaction, this Hamiltonian show some deficiencies, and then one should introduce some phenomenological correction. The group of Strasbourg Madrid has long worked on this subject, and the relevant point arising from their study is that, as a matter of fact, only a specific component of the Hamiltonian should be modified, and namely the monopole component. This work started many years ago from Pasquini and then continued by the Strasbourg-Madrid group. So we need, starting from a nucleon-nucleon potential, using a many-body theory, to obtain results comparable with those obtained with phenomenological interaction, we need to modify the monopole component of the interaction. As a matter of fact, this monopole component is responsible for the effective single particle energies. Here is the definition, and you see it depends on the occupation number and on the monopole component. The effective single particle energies represent, as a matter of fact, the evolution of the single particle energy for a system with more valence nucleons. And they are connected to the mean field of the interaction. So you can see that it depends on the occupation number. So the evolution is particularly relevant when we go far from the doubly closed shell, and so this number increases. So this group showed that only centroids, this one, should be modified to obtain results which are qualitatively comparable with that provided by phenomenological interaction. And this deficiency in the monopole component was related to the bad saturation of the shell formation properties of the nuclear-nuclear interaction, and to the need to introduce three-body forces. However, the direct use of three-body forces has been lowered, but two main aspects. No, sorry. This is just to show, to make more clear that the three-body force, the modification of the three-body forces is essentially to give results comparable with the experimental one. Here are results for calcium 49. This is we use the Kuo-Brown interaction, and here two interaction with a modified monopole component. And you may see that the better agreement is used, and this is essentially connected to the differences in the effective single particle energies, in particular to the fact that after A15, a larger gap is predicted by interaction with monopole component. So I said before, the direct use of three-body forces in the shell model has been historically neglected by two main reasons. One is the little knowledge of the mechanism of providing many body forces consistently with the nature of the nucleon-nucleon interaction. And the other one is the difficulty in handling three-body forces in many body systems whose solution require formalism that are computational extremely demanding. However, in the last two decades, significant progresses have been made as concern both aspects. For the interaction, we know that in the last decade, the chiral potential derived within the chiral perturbation theory have been developed. So in this class of potential, nucleons interact by, yesterday we have mentioned this kind of interaction, via pion exchange and strong range contact interaction, but while the long range forces are ruled by the symmetry of the QCD, the short range, which are not resolved, are absorbed in the contact terms, and where some low energy constant are introduced. So for chiral potential are organized in a systematic low momentum expansion where two and many body forces are generated on an equal footing. Here we see that at the next leading order appear three body forces, and clearly in this case we have also this low energy constant we choose for the two-body one should be consistent with the one we use for the three-body components. In most of our calculation, the two-body force is used up to the next Needing order, while only these three diagrams of the three-body forces are included. And these are reported here. We have the two pion exchange, the one pion exchange plus contact term, and the pure three-body contact interaction. In this case, and also in this case, no new parameters appears with respect to the nuclear-nucleon potential, while for these other two terms, we have two new parameters, CD and CA. So this should be fixed by using, for instance, properties of light nuclei. As concerns the second point, namely the use, how we can treat three-body forces, the procedure that is commonly used now is the normal order decomposition of these three-body components. Namely, one start from reference states, for instance, the Slater determinant, and then using the Wick theorem, the three-body component of the nuclear Hamiltonian can be rearranged in the sum of 0, 1, 2, and three-body terms. And then only the normal order 1 and 2-body components are included in the calculation. To be more specific, one includes the normal order 1-body part of the 3N interaction, and the normal order 2-body part of the 3-body interaction. And this part represents, just as you may see, the interaction of one valence particles with two whole core, and in this case, the interaction of two valence particles with one whole core. So we include these two diagrams, but the three-body normal order component is neglected. The first calculation using chiral potential and this normal order decomposition of the three-body force was performed by Otsuka and collaborators for the SD nuclei, in particular to explain the drip line in oxygen isotopes and the so-called anomaly in oxygen. Namely, anomaly means that the fact that the drip line is very close to the stability line. As you may see here, when you use the phenomenological interaction, the famous USD interaction, the binding energy are very well reproduced, and the drip line is located at n equals 16. When we use instead a microscopic nuclear-nucleon force, we see that the energies do not stop to decrease, putting the drip line at n equal to 20. While including three-body contribution, the inclusion of the three-body contribution correct this behavior and located the drip line correctly at n equals 16. And this is again related to the effect of the single particle energy, the effective single particle energy, and in particular to the spin orbit splitting between the d5 and the d3 orbitals. But now let's come to our calculation. So just here, this slide to summarize our framework. So in our calculation, we start from nucleon-nucleon and three-body force nucleons within the chiral perturbation theory framework. We use the N3 LEO NN and N2 LEO 3N. Starting from this calculation, within the many-body perturbation theory, we calculate the effect interaction. This means the so-called Q-box folded diagram expansion. The Q-box includes only one and two-body Goldstone diagrams, while then the three-body component included only the one-body term, the first-order terms. Then in our calculation, we include only some density-dependent two-body contribution to account for the fact that usually the interaction is calculated only for two valence nucleons. But then when we go far from the doubly closed shell, we have to take into account for other correlations. And so we include this density-dependent contribution. Calculation I'll show here are for P-shell, and we have performed calculation for P-shell nuclei and FP-shell nuclei. As a matter of fact, for P-shell nuclei, we use this calculation to benchmark our approach, and so results are compared with those of no-core shell model calculation. Here I have reported results for boron 10 and boron 11 using only the NN force. And you may see that results of realistic shell model and no-core shell model are very close, but they are not able to reproduce the experimental spectrum. This means that our approach, the approximation we have to consider in our approach are quite reasonable. So we include also the three-body force, and as you may see now, for boron and 10 and boron 11, both realistic shell model calculation, no-core shell calculation, give a good description of the experimental data. As you may see, discrepancies between the two theoretical approaches are not so good as in the NN force. And this is because in our calculation we include only first order diagrams of the three-body components. So here I have reported the effective single particle energies for the proton and neutron case. And as you may see, this effective single particle energy rapidly drops down when considering only the NN force. Why? When including the three-body forces, the gap between the spin orbit splitting of the P-shell remains almost constant, about 4-5 MeV, which explain the results I have shown before. So three-body forces are essential to make explicit the spin orbit splitting in the 0p orbital and ensure better closure properties. Here are some results. We have calculated all nuclei of the FP shell, but here I report only those for calcium and nickel isotopes. Here are two neutron separation energies, and here the excitation energy of the first 2+ states. Red results represent the experimental one, the blue one only those obtained only including the two-body forces, and the black one those including the two and three-body forces. As you may see, until 28 results are very close, but then from 28 to 30, the two-body force only is not able to reproduce this drop. And the same is true for the shell gap at n equal to 20. I have also reported in pink this force that is obtained by removing from the NN force the monopole component and adding the monopole component we obtain with the three-body forces. And as you may see, the black and the pink line almost overlap. This means that the hypothesis that three-body forces essentially affect the monopole component is confirmed by our calculation. This is also true in particular, more than for calcium. Results for nickel isotopes confirm this picture, and in particular you may see that including only three-body forces we are not able to reproduce the doubly closed shell nature of nickel 26. Here I have reported the effective single particle energies, those with the two-body force and three-body force, and you may see that a significant difference is found for annual 28 and for, when including three body forces, a significant larger gap between the F7 and the other orbitals is obtained. This is related to the monopole component, and in particular to the repulsive nature of this component. Namely, I have reported here some matrix elements entering in the nickel calculation, and you may see that three body forces provides a repulsive contribution to all matrix elements, which makes the neutron-neutron and proton-neutron matrix element less attractive and the proton-proton more repulsive. However, the size of the contribution depends on the involved orbitals. It is different on the matrix element with respect to the matrix element we consider, and so this produces substantial change in the spacing between the effective single particle energies. Just to slide on a new work we are now doing. So we have assessed the role of three body forces in shell model calculation, and in particular its repulsive nature that is responsible for evolution of the effective single particle energies. But we may wonder, what is the specific mechanism that produces this effect? So in this context, we have made a tensor decomposition of the chiral three body forces. This means that we have developed the three body force in terms of the tensor operators in the spin space, in the momentum space. This work was essentially made by our collaborator Tokuro Fukui, and you may see here that the two-pion exchange is the only component that contains the 0, 1, 2, and 3 rank parts, while this one contains only the 0 and 2, and this one only the 0 component. Here I have reported the effective single particle, not the single particle energies, namely the spin orbit splitting between the P3 and P1 orbitals, including only the two body forces, and then this one are obtained by adding all the different rank components of the three body forces, 0, 0 plus 1, 0 plus 2. As you may see, the central component does not affect this spin orbit splitting, but the major contribution is given just by the rank 1 component. This means that the spin orbit splitting induced by the chiral three body forces is primarily governed by its rank 1 component, and this means, if you remember the picture I showed before, it is connected to the two-pion exchange term. The same thing we can see by looking at the effective single particle energies. We can have the same conclusion, but I don't show you. And so, just my summary. So I have shown that genuine three body forces provide a repulsive contribution, which, although partially counterbalanced by the induced three force, is essentially in determining the location of the drip line and the evolution of the shell structure. The three body force affects essentially the monopole component and confirms the need to introduce monopole adjustment when using effective shell model Hamiltonian. The size of the contribution depend on the involved orbitals, ranging from 10 to 200 kV, which substantially changes the spacing between the effective single particle energies, and then a crucial role in the spin orbit splitting is played by the vector rank 1 arising from the two-pion exchange component. These are the collaborators, and thanks for attention and for your patience.
Thank you very much, Angela, for this very nice talk. Are there some comments, questions? Yes.
What about the fusion reaction or the fusion reactions working on shell model? Is there any new working shell model with fusion reaction or fission? Fission.
we had also yesterday that I asked, remember, usually in this kind of reaction, you use not the shell model in its complete form, namely the interacting shell model, but just the mean field. They are quite complicated calculation. As you may see, we have to perform a calculation in a reduced space. Also, you take 5 orbitals, dimension of the matrix, and you consider a complete calculation are very, very big. So I don't think that at the moment this kind of approach can be used for study this,
Thank you.
this
Only
kind of reaction.
pairing effect only, shell model in fission reaction, shell model. Yeah, no, thank you
No,
very much.
maybe you may
I-
use the more simple form of the shell model, namely the mean field that is at the basis of the shell model.
Did you try to apply your model in nuclear matter calculations?
Yes, sure.
What about the results?
There are good
The
results.
question of state is more
Yes,
stiff.
We are able to reproduce. We have
Nuclear matter.
Yes, nuclear matter. Yes, yes. There are papers. I haven't shown here, but if you want, I can give you the references
Okay.
where we have applied. We have applied, as a matter of fact, at the moment, because it's a long time we work in this field. And at the beginning, we use those kind of potential derived within the meson exchange theory, namely CD bond, for instance. And they are very good. Then now we are trying to use the chiral, but for chiral, it is more essentially to include also the three-body one. Because, you know, maybe in some interaction like this one that CD bond, some effect of the three-body one are already included in the two-body parts. But in this case, and you don't use, for instance, for chiral potential, you don't, when you use a bare potential, you have to start from the bare, then you have to construct, for instance, the G matrix, or the VLOK as in the model calculation, but in the case of chiral potential, you can directly construct potential within a low momentum space, and so you are not constrained to use this technique to normalize the potential.
Okay, okay, thanks.
Thank you, Angela, for this very clear presentation. I have a couple of questions. One is about three-body forces, because you show that there are lots of indications and hints that we really need three-body forces in nuclear physics. But, I mean, it would be very good if we have a fundamental proof in a tritium or helium-3, because that, I mean, in a many-body system, three-body forces are merged with a lot of other things. The key aspect could be the fact that the tritium and helium-3 cannot be described without a three-body force, only with...
No, it cannot be described.
Yeah.
So you are constrained. There is the Tyson line.
Yeah.
Do you remember that usually if you use only two-body force, you are not able to reproduce it. So I think that clearly, as I tried to show at the beginning, that calculation for light nuclei are the most important to specify the role and also the interaction we have to use. Because maybe I don't remember, Vasily shown yesterday the fact that maybe we have not the correct interaction. So no Korshel model or green function Monte Carlo model that can be used for light nuclei are very important for this aspect. Here, clearly, we have a lot of nucleons, as you said, effects are mediated by other aspects, but we have seen that especially for exotic nuclei, namely when this occupation number increases, the evolution is very relevant, and the effect of three-body forces.
And then I have another small question, because you show that the pion-pion mechanism is very important for
Yes, it
spin-off.
seems so.
Yeah.
It seems so. We have just,
Yeah.
these are just not
I-
published, and
I see an interesting analogy with, you know, with the double charge exchange, where you have two pions again, which are exchanged, and you have the problem whether these are correlated or not correlated, and so on. Because now I see 3 nucleons and 2 pions, which I mean are shared. The question is, in this 2 pion mechanism, the pion-pion correlation is included or not, or is only nucleon, pion, nucleon?
this is the diagram is this one.
Yeah.
So you have the exchange of 2 pion, as
Yeah.
you said.
And the 2
not
pions are not,
sequential,
are-
sequential. Your language.
yeah, but the 2 pions are not interacting each other, no? That's
No, no, no,
Yeah.
no, no, no. The pion mediate the interaction between
Yeah.
nucleons. So this
But
is
there is no
this
pion,
is
pion,
based,
yeah.
the chiral potential are constructed on this basis.
okay.
Since we are getting short of time, I guess we
We can go.
should thank our speaker again.
I would like to thank very much to the organizers, to the committee, especially Dr. Pacu and Dr. Suliotis for inviting me, and it's a very nice thing to be here. Okay, so now I'm going to show my presentation. That is a database research project. I am an NSDEF nuclear structure data evaluator. So this is a work done in under the data project. So, namely, could revisiting the principles of a level scheme bring new insight into high-spin physics? So, our presentation is divided in 3 parts. First is experimental evidence of the property which triggered all this work. Second is a level scheme reconcept, and third is the insight into high-spin physics. So, the experimental evidence, our case study is the 171 ytterbium nucleus high-spin rotational bands with a number of structures of which most are double signature partners. So how the bands can be described by the Bohr-Mottelson collective rotor? We have the well-known I/1+1 rule and also the inverse proportionality with the moment of inertia. We denote all this parameter with, sorry, I mean, I didn't start the pointer, so how shall I start it? Oh my goodness, that's a, because you cannot see my mouse, so I need the pointer, please. How to do it? Yeah, I guess I found it. Laser. Okay, that's good. Sorry, because I thought you see my my things, but you didn't. So okay, so starting again. Yeah, this is the well-known I/1+1 rule. With the inverse proportionality of the moment of inertia, we denote this parameter as C inertial parameter. Now, the difference between 2 gammas, two levels gives a gamma ray energy, which is linear in the spin and also depends on the moment of inertia. The difference between 2 consecutive gamma rays, it's 8c, so it's no longer depending on the spin, but only on the moment of inertia. Now, if we have an ideal rotor, all these dependencies are going to be sharp, so that's a pure parabola, that's a pure linear, and that's a constant. Now, I would like to use the last relation of the delta gamma as a magnifying glass. What I'm doing this delta gamma x, delta gamma y differential coincidence metric, so it's a simple thing. I'm taking all the coincidences in the level scheme, and I am doing the differences in between each pair of coincidences. So that's a differential coincidence matrix-like pattern. And it's a bitmap distribution because I have only positions and not intensities. So what is resulting is going to be something like that. So now it's a 2D representation of this regular grid of 8C. If for the ideal rotor, we have statistics concentrated only on the crossings of the grid. Now, if we take real bands, we'll have fluctuations due to the moment of inertia, and that's going to produce fluctuations of the statistics surrounding the centers. On average, we'll keep the 8C grid, but with a modulated pattern of maxima. What we do get instead is something unexpected. And what is that? It's a double structure of imbricated maxima. So we get the 8C, which we can see here in green, but we also get the secondary structure of maxima, which is placed as a quarter of AC, namely 2C. So that's an important thing. It's a very simple experimental or data fact, actually. And that's going to bring this, I called it a new property, which is repeatability, which is exactly this imbricated structure of the main maxima and the secondary maxima. With that, how can we trigger, how to keep track of this new evidence is by adding a k integer number into the original distribution of energies. That's going to propagate the new regularity into the energies. So now we see that we have the 2C moment of inertia. It's a real number parameter. And we have now the angular momentum expression, which is an integer number quantity. Next, I'm going to show you that this is not a sparse property, but is rather the rule than the exception. And how is that? So this is a representation of the E gammas, experimental gammas versus spin. Now we can see that this is pretty much as the ideal dependence. So it's a linear dependence with deviations from the straight lines, especially the bands number 3. The other bands are mostly like a quasi-linear beam of almost parallel and equidistant lines. Now, on average, we can describe that by how? Simply having a slope and doing the different offsets of the band. So doing that, we also should add a k integer number in the parametrization. But what does it mean? It means we get exactly the same formula as before. So this is our repeatability property now seen in this kind of patterns. But what does it mean? These plots are the common thing in high-spin physics. All the level schemes show a plot like that. That means this property, it's indeed an ubiquitous property of nuclear data. It's high speed. So now, how we determine our parameters, the slope, and the case through a least square fit with this formula, of course. And once we determine the average slope, that's determining an effective moment of inertia, which would be a single value, a constant value, characterizing the average motion of all these real rotational bands. Now, these are the results of the fit. We have the particular fits for each of the bands. And now we have the slope and the effective moment of inertia. And here I am bringing the fitted straight lines. And this is now a generalized ideal rotor or rotational bands, which basically captured the average rotational behavior of the real bands. And now I'm going to show you a level scheme for this time of ideal bands and for the real rotational bands. Now, second part, level scheme reconcept. So we start with our generalized ideal rotor bands. And we see that for K0, we have the pure Bohr-Mottelson ideal rotor bands with the even and the odd bands represented here. That's already a prototype for a level scheme. Now, for K non-zero, there's a whole bunch of bands. And these are going to be now all share the same effective moment of inertia, but are no longer described by the Bohr-Mottelson rule. How to place the K generalized ideal rotor bands into the level scheme? That's the question. And how to place now? Usually people just take and build a level scheme band by band. We are not doing like that. So I am simply taking this property and transpose it in the level structure. That's going to generate a geometrical structure on which the bands are going to be superimposed at decay paths. So the answer to the question is by adding 2i+1 stairs in steps of 2c to the Bohr-Mottelson rotor band. So with that, we get this parabolic 2D building in which the bands K0 are vertical paths and K non-zero are just tilted paths on this structure. Moreover, we can index all these levels by 3 numbers, which is which is I, which is a nuclear spin, which is M, is a position of the stair relative to its range, and N, which is the energy of the level in terms of 2c, that's also an integer number. So now we get a triple coordinate of integer numbers. So that suggests a 3D picture. That suggests a 3D picture. And before I'm showing you how we get that, I'm going to tell you we got 2 things here. The old thing, which is a Bohr-Mottelson quadratic dependence, and that's described by the 8c, and the linear scale, and that's given by the extra 2c regularity we saw. So now it's a combination of 2 things, an old one and a new one, and they are going to be integrated on a 3D picture. How we get the 3D picture? Easy. So we have this open structure. We take it and shape it like a parabolic tower. Now the stairs will run in along the walls of the towers. What we get in a view from above is this structure of a double helix. So the level scheme now is commensurate with a double helix structure. So we have the black curves here hosting the even spins and the red ones, the odd spins. Actually, the structure is only the discrete ones. We don't have, the lines are only guiding the eye. We are still in quantum realm, so we need the discrete points. Now, these are the finite structures of the double helix. And we have the 2 types of double helix. One for the even spins, and for the even A nuclei, and one for the odd A nuclei, even and odd. Now, we have basically what I did here. I took only the counterclockwise rotation as conventional rotation. We also can bring the clockwise rotation. Now we have only these 4 situations for combinations of spin parity in high spin physics. This combination can be hosted on the blue helicoid and the other one on the magenta helicoid. So with that, and same thing is about the odd A nuclei. With that, I'm going to step again and make another step of our new parametrization, and that means the decomposition of experimental gamma rays. So what we have here, we have the straight line and a point, which is the experimental point. Now, how I'm decomposing that? I am taking the value from the fit, which is this, and I'm taking the deviation. But I decompose the deviation into a k prime, which is an integer number and a fractional number, okay? So with that, what I'm doing, why I'm doing that? Because I always want to keep straight the dependencies, to have the angular momentum part as an integer, and to have the moment of inertia as a real parameter. Now I can show you in this parametrization how the band's moment of inertia, now we modified a bit the definition of the moment of inertia, so we take the average value and multiply it by the particular number, so we'll get a band moments of inertia. And this is a pattern. They are now waving functions around the effective moment, which is the average rotational behavior. Now with that, we got a complete description of the experimental bands based on the new setup and the new parametrization. And now I'm going to show you the level scheme for the 2 types of bands. First, this is the generalized idea rotational bands. I take a ground state band and I'm running I and K, and this is how it looks like. So this is a full set of, this is a 3D new level scheme type, and this is the view from above, and these are lateral views from the front face and from the right-hand face. What we can see here, for K0, we have a straight line, that's a band now, which is superimposed on the double helix. K0 is that, K1 is that, K2 is that, K3 is that. It's only following the two X and Y directions. Going with negative values, K0, K minus 1, K minus 2, K minus 3, doing the same thing but in reverse order. Now we have the odd values on the y-axis, along the y-axis, and the x values along the x-axis. And that's it. Now, what we do here, we have k plus k prime, which is coming into, and a change in the definition of the moment of inertia. But look how the level scheme looks like. So it's a simple change in between that, and that's an ideal rotor-like behavior, and that's a real band, real nucleus level scheme. Looks how much varied is that, and how the bands now denses on the double helix, and basically that's bringing precession of the bands onto the level scheme. The third part, insight into high-spin physics. So we have this typical situation, and that's an important thing because that points the things here. So we have this elementary helix loop with gamma transition analysis. We have the previous two situations shown here. Now, in our classical level schemes, we have an initial and a final level and the gamma ray. Now we have that, but united by the loop of the double helix. What we first do, we can define a phase angle for each of the discrete points which are on this structure, and we can define a phase shift, which is a difference. Now, we have this typical situation. That corresponds to the first ideal pattern. We have transitions in between levels which are going to be directed along the diameters, basically. Now, delta theta 0 means we have no k plus k prime, and that's going to be an elementary helix group of 2 pi. And that's certainly done by only the 2i. We have no k's. So that describes the macroscopic rotation of the collective motion. And this is kind of the participation of the rigid body to the rotation. Now, when we have k's which are are present, the k plus k prime enter into scenes now. We have delta theta non-zero. That's going to produce these precessions, either counterclockwise or that's clockwise or counterclockwise. And that's now bringing, basically, that's a microscopic intrusion into the macroscopic rotation. So it's the same picture of having a macroscopic described by the 2i and the microscopic described by the k plus k prime. And that's going to be to bring precessions of the bands. This is a collection of the phase shifts we got in this nucleus. We have these situations. In high excitation and spins, we have clockwise intrinsic rotation, and in the lower part we have counterclockwise rotation. In between we have a phase transition like in solid physics state or state physics. That means the nucleus first rotates clockwise, the intrinsic structure, and after that go to counterclockwise. When the crossing of the band is sudden, we'll have a sudden backbending. When the bands align points, we'll have milder backbending. That's seen here. High excitation and spins, all things go clockwise. In the lower part, all things go counterclockwise. Now we see that bands number 2, number 3 have a sharp backbending, the others have a milder backbending. Another interesting thing, in the last part, counterclockwise, all coalesce towards the big arms of the level scheme, which are the ground state bands. We see all coalesce down. Now, my summary is simple as 1. This is repeatability sampled into the data. This is the double helix structure resulted from that. And this is the double helix level scheme. It's simple like 1, 2, 3, and that's a certain thing. Now, the conclusions. So the double helix added this semi-classical meta trajectory of the level scheme. On average, we can suppose that the nuclear matter itself follows somehow the trajectory of the double helix. And third, through repeatability, nuclear matter's double helix motion can be seen as a vortex motion. So that's bringing vortex into the liquid drop. So that means we can have vorticity in the liquid drop, which can relax the Bohr-Mottelson hypothesis. So that's, I guess, a pretty new landscape which can emerge from that. But is that vorticity so unusual? Not at all. It's everywhere in the universe. We have it in the galaxies, we have it on the Earth, we have it in the land of the living, we have it even in the DNA. And now we can signal it in the atomic nucleus. That's the tiniest of the scales where it can be. But look how much this resembles a galactic motion. But we still have the broken arms of the Big Bang, which is a quantum effect. So that means we are now in this position to say that perhaps double helix is a structure of the nuclear structure itself. And that's my presentation. Thank you.
Thank you very much, Professor Nica, for this very intriguing presentation. There are some comments.
Yes, thank you very much. It's really exciting what you present. Just a question. In your presentation, you did not mention about vibrations, because typically these nuclei rotations and the gamma and beta vibrations couple together, and inertia momenta also are affected by this. And instead you only mention single particle contribution to the rotation. So why you did not talk about vibrations?
Yes, because there's no time to.
Ah, okay.
I mean, that's a very preliminary presentation. And that's a data-based presentation.
No, of course.
So I'm not speaking as as a physicist of the nuclear structure, but as a data specialist.
Yeah,
so
but
that's simply finding a new kind of property in the experimental data and transposing it.
That's great.
That's the first stage. The interesting thing is that what I suggested there is we can retrieve the big stage of what we know. Macroscopic in the 2-pi rotation and microscopic in bringing the precession of the bands. After that, all is there. But the interesting thing is non-contradictory with the known physics. Because it basically does not touch anything from what we know, but add an extra pattern. So whatever is valid now in physics should be visible here in a way or another. But now this brings the new setup, which is a very nice semi-classical unifying picture. I guess that's the thing here.
But you talked about this, but you only mention Ytterbium-171.
Yes.
So could be very, very important to have an extended
It's
vision.
exactly that. I have 7 level schemes in this. Great. Even, you know, if I've shown you on what's that, an Erbium 160 with tons of bands. That's a simple case, and that's a didactic case. But if I'm showing you a large level scheme, you'll see things there, which will quite impressive. Now, why I'm showing that? Because I want you people to do that. I mean, if people do that, that's going to be a kind of new ideas, you know. So if people will ever use that, that's going to generate maybe some, it's a complementary thing, but maybe some things will be better visible here. For example, it's introducing naturally a direction of rotation in nuclear physics. Even that we can define a clockwise and counterclockwise is quite appealing. And even I showed you conventionally is a clockwise, but we can use both. So we have a set of 4 helixes going in both directions. What is that? Tell me. So, but it's a natural representation now of you can see the rotation. So where's that bringing? Where's that going? I don't know.
Since we are running short of time, maybe we have to defer further question to the work, to the parallel sessions. So let us thank our speaker again. And, our next speaker is Dimitrios Petrellis from the Czech Academy of Sciences, and his subject will be nuclear shape phase transitions in the regions of 40, 60, 90 neutrons.
Okay.
Sorry, is it in presentations? Oh, it's here? What is it?
And it's a
Control
PDF.
PDF.
Yes.
Okay, first So first I would like to thank all the organizers for the kind invitation, and especially Professor Athina Pakou. Let me say that this work was just recently submitted for publication and is currently under review. It is so I will be talking about nuclear shape phase transitions in the 40, 60, 90 neutron regions. It is the result of a collective effort of the people you see here. Unfortunately, as you see here from the dedication here, one of our colleagues is not with us anymore, Adam Prasek, and we feel that we should dedicate this work to his memory. He was the youngest member of our group, an excellent student of the Technical University of Ostrava. Coming now to the other collaborators, Petra Alexa from the Technical University of Ostrava. He was the supervisor of Adam. Dennis Bonatsos, who is here from Demokritos in Athens. Me and Petr Vesely from the Nuclear Physics Institute of the Czech Academy of Sciences, and Gabriela Tiamova from the Polytechnic Institute of Grenoble. So, first I will talk to you about how these structural changes manifest themselves by examining certain experimental quantities and how they evolve with neutron number. Then I will show you a qualitative interpretation in terms of simple shell model arguments. Then I will present you some results from microscopic self-consistent calculations, and then some results from macroscopic algebraic collective model calculations. So, one of the benchmarks of benchmark quantities of nuclear structure is the R4/2 energy ratio. So it's the energy ratio of the first 4+ state over the energy of the first 2+ state. And you see here, I don't know how visible it is, that at 90 neutrons for these nuclei, neodymium, samarium, gadolinium, and dysprosium, the R4/2 ratio jumps from around even less than value less than 2. It jumps to over 3, and it stabilizes around 3.3, which is the rotor characteristic of a rotor value. So it jumps from a spherical value characteristic of spherical vibrator to that of a rotor. For these nuclei, and let me say that these are, let's say, typical examples of the so-called X5 critical point symmetry. Now, in other other region of the nuclear chart, in strontium, zirconium, and molybdenum, something similar happens at n equals 60. Again, from less than 2, it jumps to over 3. We will see especially zirconium and molybdenum that we have examined. We will see them later. And finally, in zinc, germanium, and selenium, something similar, especially selenium, happens at n equals 40 or 42, this sudden increase in the R4/2 ratio, although it doesn't reach the rotor value of 3.3. And here you see the differences, how they spike at these neutron numbers. Another key quantity is the B2 from the first 2 plus to the ground state, yes. And again, here you see something similar, a sudden increase around the same neutron values for these nuclei that I showed you before. Now, the energy ratio of the first 2 plus to the excited 0 plus shows a decrease. Let me say that from what we have seen until now, this picture points to a lowering of the first 2 plus. So this is also what is happening here at n equals 90. Here also, although the data are not so complete here, and here also for selenium, it starts to rise and then it drops down. So all these sudden changes are signs of some kind of phase transition. And finally, the energy ratio of the gamma, of the 2 plus of the gamma over the first, over the 2 plus of the ground band show again the same trend in the same numbers for neutrons, 90, 60, and 40. And again, suggesting that the first 2 plus, the 2 plus of the ground band drops suddenly at these neutron values. Now, in the 1970s, Federman and Petel proposed a mechanism to explain this phenomenon. This is very nicely presented in Rick Kasten's book, Nuclear Structure from a Simple Perspective, and also refinements of this mechanism appear in recent reviews of the shell model. So the key point of this mechanism, proposed mechanism, is the interactions between valence protons and neutrons. Another key point is that at mid-shell is an area of maximum collectivity and hence deformation, and also of lowest lying 2 plus states. But the question is now, where is the mid-shell? Because the shells are characterized by subshell structure, by gaps that open and close depending on the number of protons and neutrons present, which means that, as Professor Gargano mentioned, it suggests the concept of effective shells. So, for example, for around 60 protons and 90 neutrons, what we have is that for less than 90 neutrons, we have an effective proton shell from 50 to 64 protons. There's a subshell gap at 64 protons. So the mid shell lies around 56 protons. But as the neutron orbital, as this neutron H9 half begins to fill as we add neutrons, then the monopole proton-neutron interaction between this spin orbit between this orbital and its spin orbit partner in the protons, the H11 half, results in a sudden drop of the H11 half proton H11 half, eliminating this subshell gap. The result is that now the new effective proton shell is the standard, the normal 50 to 82 protons. There is a new mid shell. The position of the mid shell has moved to higher values, 64, 66, and this affects nuclei with neodymium, samarium, gadolinium, and dysprosium that I showed you. It's very, this is made obvious if one looks at this series of isotones, N88, and how the first 2+ state evolves in this. So for example, you see here that for N equal 88, in this starting from xenon and ending in ytterbium, we see that the minimum of the 2+ is in barium, let's say, but when we add 2 neutrons, immediately the minimum moves to samarium, and we have here neodymium, samarium, gadolinium, and dysprosium, where this drop is really impressive of the 2+ state. And this concept of valence nucleons, I think, is also important in the proxy-SU3 scheme, as we will hear from Dennis Bonatsos in the next talk. Now, we performed microscopic calculations using the Hartree-Fock equation with a Skirm effective interaction and coupled with BCS equations. We used the code SkyAx that uses as the initial single particle states Nilsson orbitals. We examined about 15 Skirm parametrizations, but the results that we got for these are not, they don't differ so much from each other. And if one performs what's called constrained calculations, fixing some quantity, in our case we fixing the quadruple moment, and finding the value of the ground state energy every time, one gets potential energy curves, which show how the ground state evolves with the deformation parameter beta. So here we see for the potential energy curves for selenium isotopes from N equal 34 to 46. And this is for two different parametrizations, which are very similar. You see that the minimum, so we begin with an oblate minimum that evolves into this intermediate, let's say, shape, and then to a prolate minimum, and at n equal 40, we have this intermediate shape here. For zirconium isotopes, we start with a spherical, typical spherical shape, and then slowly an oblate minimum starts to form, and a prolate minimum at the same time. The picture is very similar for the molybdenum isotopes. First spherical, centered around a minimum around 0, and then the oblate and then the prolate minimum start to develop. For neodymium isotopes, we have this kind of flat, we start with this kind of flat potential energy surface, and then simultaneously one oblate and one prolate minimum start to form, with prolate minimum being more pronounced and more sharp, finally. Now, Petrellis came up with the idea of using this index that uses the occupation probabilities of the resulting single particle states, and it shows us what kind of levels dominate the Fermi surface. It can evolve into a useful tool of analysis, this one, and we see, for example, here in neodymium how the proton, I think it's the proton, yes, proton negative and positive parity orbitals, although they start by dominating, they fall down. Now, we performed macroscopic calculations using the algebraic collective models. It's a tractable version of the collective model of Bohr and Mottelson. It has the kinetic energy term, which has a beta part and an angular, a radial and an angular part. And the potential is all these terms that are compatible with the symmetries of the Bohr-Mottelson Hamiltonian. So we have even powers of beta, both positive and negative, odd powers of beta accompanied with cosine 3 gamma, and also squares of cosine 3 gamma accompanied by even powers of beta, both positive and negative. If we use as basis wave functions irreducible representations of SU11 for the radial part, for the beta wave functions, coupled with 5-dimensional spherical harmonics, irreducible irreps of SO5, then we have analytic solutions of this Hamiltonian, and by fitting this parameter to data, we can have, for example, energy level schemes that, when compared to experiment, these are theoretical, these experiments are not so bad. With the exception of zirconium, we couldn't fit zirconium well, so I'm showing you only neodymium, molybdenum, and selenium. And one can decompose, let's say, this. So if one wants to plot the potential as function of beta, this is what one gets, for example, for neodymium. This is the total potential, but it's useful to decompose it into different parts. For example, the beta even parts for only positive powers of beta, and then beta even with negative powers of beta, beta odd part only positive and with negative. And here you have the beta even and beta odd, thank you, Dennis, result. We can do the same for molybdenum and selenium. What we observe is that these potentials resulting from ACM calculations show similarities with the potentials used in the Bohr Hamiltonian in the context of critical point symmetries, like, for example, displaced infinite square well with a sloped wall, Davidson potential, Kratzer potential. And now my summary. We saw that certain experimental quantities has energy ratios, B2 transition rates, serve as benchmarks for nuclear structure. The valence proton-neutron interactions are a driving force behind structural change. The microscopic calculations in the 40, 60, 90 neutrons regions show signs of first-order phase transitions with coexisting minima. And the potentials we got from our macroscopic calculation show similarities with potentials used in the context of critical point symmetries. Thank you very much.
Thank you, Dimitrios, for this nice presentation. Are there some comments, questions? Oh, please, Vaya.
Thank you, Dimitrios, for this nice talk. So you mentioned that you have a parameter that you fix each time. There is a slide, not there with the potential.
You mean in
there.
this?
Yeah,
all
these parameters. How do
Yes.
you fit this one?
Yes.
I
how
mean,
we-
because, yeah, I mean,
all these parameters.
so you have to
Yes.
fit all of them.
Yes. So actually, this is work done by Gabriela Tiamova. So she's experienced in this algebraic collective model.
Okay.
And she knows the role of how to use the impact of each parameter, let's say. So,
Okay.
kind of she put this, she did it in a critical way. I mean, it is not, so we don't have, we didn't have a fitting like, you know, so she played with these parameters and she fine-tuned and she was able to reproduce.
So she's
the
tuning the
spectra.
parameters
Yes,
according
yes,
to the
yes.
results, like by hand, each time she tries some trial and error.
Exactly, yes,
Okay.
yes, yes.
But is there any physical, for all these terms, are there physical, let's say, meanings to that? Or it's just how you parameterize your Hamiltonian?
Yes, there is.
So you can
There-
attribute
yeah,
physical
yes.
properties to each of
Yes,
these
yes, yes. You can
origins.
find in the book by Rowe and Wood,
Okay.
all these are mentioned in this, so the physical meaning of each one. But here, for example, we can recognize, for example, that the Davidson model that we have used with the Bohr models on Hamiltonian, for example, is parameterized like, okay, each term has different coefficient here,
Yeah.
but I mean, it's still solutions of the Bohr Hamiltonian, and the physical meaning of each parameter can be found here in the book
Okay.
by Rowan.
But I'm sorry, I think I have many questions.
If I'm allowed
Okay,
to
maybe I
comment
should
here.
leave it for the session afterwards.
If I'm allowed a comment here, the way to see the meaning of these parameters, of these terms, is to plot them separately in the potential
And
and the
yeah,
surface.
yeah.
Then you
exactly.
see which
Contributes at
quantity is
this.
influenced by each of the terms and so on.
Yes.
And actually, Gabriela has done that in other papers earlier, so
Yeah. So
it's
some
not given in this paper.
I'm sorry, yes. So some parameters, for example, may define, let's say, the scale of the ground band. Some parameters.
So is
the
this for
scale,
each nucleus again?
sorry?
I'm sorry, I'm interrupting. So she does the fitting for each nucleus, like I want now to find the spectrum for
Yes, it's
neodymium,
here.
let's say.
It's here. It's here.
Okay, okay.
So the values of the parameters for each nucleus are here, here, and here. Each nucleus is fitted
So you need
separately.
the
Yes.
spectrum of
Yes.
your nucleus from the experimental data in order to find the parameters,
Yes.
right? Okay.
Yes, yes. We fit. It's fitted on the spectra. So as you said, the scale is given by one parameter. Other parameter may play important role in the position of the beta band, how low it get of the beta
Okay.
band head.
No, because if, since they are using a skerm functional, in principle one could do the potential energy surfaces and then put, and make this Bohr Hamiltonian using the mass parameters and the collective moments of inertia from the skerm.
Yes.
So
yes.
this is why I haven't seen that before,
No,
so why?
Yes, yes. It's not so simple because you see how it looks. It has some features, some terms that contain negative powers of beta were important in order to achieve the fitting. And you see, for example, how they look. They resemble more the potential used for critical point symmetries within the Bohr Hamiltonian. But it is one of our, let's say, we want to find a connection between the macroscopic and the microscopic. So it's one of our goals to work towards that.
Thank you, thank you.
Are there some other comments or questions? If not, let us thank our speaker again. And I would like to pass the chair to Professor Minkov.
Okay, I take some short responsibility to present the next speaker, who is Professor Bonatsos.
Και πώς κατεβάζουμε την οθόνη?
And Dennis will speak about 7 years of the proxy-SU shell model symmetry.
Το ποντίκι. Και ευχαριστώ πολύ. So I will give you a brief review of how the proxy-SU cell model symmetry has been developed over the last 7 years. Actually, the first time this new model was presented was 7 years ago here in Ioannina in one of the earlier versions of this workshop. I'm working in Dimitrios, and the people behind this work are Andriana Martinou in Dimitrios and Spiros Petrellis, Theomar Zimekis in the University of Athens, and Nicolay Minkov, our chair. There is a long review article published last year on this model, which you can find in the journal Symmetry. Briefly, I will try to describe the following points. How the proxy-SU scheme was introduced, how you can restore the SU3 symmetry in the three-dimensional harmonic oscillator, and then how we justified the proxy-SU3 symmetry in the framework of the Nielsen model, and then in the framework of the spherical cell model. Then a concept which is very important in this framework is the highest weight irreducible representations, which I will explain briefly. And the dominance of these representations has very important consequences. It is the origin of the prolate over oblate dominance in the ground states of even nuclei. Also, it is the origin of the prolate to oblate shape transitions in the heavy rare earths. Other consequences are islands of the shape coexistence. Shape coexistence cannot appear everywhere, but only on certain regions on the nuclear map. And also, I will discuss briefly the recently very hot topic of preponderance of triaxial shapes in medium mass and heavy nuclei. So, very briefly, the basic idea between the proxy-SU symmetry is that you replace these intruder orbitals by the deserting orbitals, which because of the spin orbit force has gone to a cell lower. So as you see here we had this DG cell. This bunch of G orbitals has abandoned the cell, and there is a bunch of H orbitals coming down from the next cell, the PFH. And this destroys the SU3 symmetry. But it turns out that it is a very good approximation to replace these levels here by these levels. This is justified in what I'm showing, I will show to you in the next transparencies. It is not obvious, but it is a very good approximation. Actually, in terms of the Nielsen scheme, you can see this in the following way. Before making the approximation in the usual Nielsen scheme, if you write down the matrix of the Nielsen Hamiltonian, you see that you have a part in the upper left part where you have non-diagonal matrix elements as well, and you have also the lower right part where you have only diagonal matrix elements because the interaction cannot connect states of opposite parity. When you make the approximation, the proxy-SU3 approximation, this table becomes like this. The upper left part looks like before. The lower right part looks more or less like before, but you here have some, in the upper right part, you have some non-diagonal matrix elements which did not exist before. This is the price you pay in order to make the approximation. But as you see, these matrix elements here, these numbers are much smaller than the numbers on the diagonal. So this means their influence is very small, and this is why the proxy-SU3 approximation is good. The next step was to justify the proxy-SU3 in terms of the spherical cell model. This has some mathematical procedure behind that. You connect first the Elliott SQ3 cell model to the cell model to the spherical cell model basis. This is a well-known way how to do that through unitary transformation. Then you connect the cell model basis. Instead of using L and M, you use the L and J quantum numbers. This can be done through Clebsch-Gordon recoupling, no problem. So then this way you connect the Elliott cell model to the spherical cell model. And it turns out that the proxy-SU3 is equivalent to unitary transformation between the intruders and their proxies, which I was showing you before. So it's a mathematically well-defined procedure how to make this correspondence. Then what is very important is the dominance of the highest weight irreducible representations. You can think of them as the most symmetric irreducible representations, the most symmetric configurations, which is allowed by the Pauli principle and the short-range nature of the nucleon-nucleon interaction. I'm not going into the details of how you form the wave function, but these are the basic ideas behind that. You have the Pauli principle present, the short-range nature of the nucleon-nucleon interaction, and this forces the nucleons to go into the most symmetric configurations, most symmetric reducible representations in the language of group theory. And this has many important implications. First of all, it explains the prolate over oblate dominance in the ground states of even nuclei. Here is a table of the irreducible representations occurring in heavy rare earths. As you see, most of them are prolate, which means you have irreducible representations in which the first number is larger than the second number. There are very few in which the opposite is happening, where the second number here is larger than the first one. These are underlined, and they mostly appear in the lower right part of the table. So you see that in this specific region, you have many prolate nuclei and very few oblate ones. And this happens also in other regions. This is explained in terms of the proxy-SU3 approximation, just using the Pauli principle and the short-range nature of the nucleon interaction. No parameters, no fitting, no other approximation. Also, the model without using any free parameters predicts a transition from prolate to oblate shapes around 114, 116 neutrons in the heavy rare earths, and there is strong experimental evidence that this prolate to oblate transition is really seen there. Also, if you look into the details, the proxy-SU3 symmetry through what is called the dual cell mechanism introduced by Andriana Martinu a couple of years ago, it shows that you cannot have a safe coexistence along the whole nuclear chart, but only within certain stripes which appear in this transparency in red and blue. So you cannot have shape coexistence everywhere, but only within those stripes. If you compare to what is happening experimentally, you see that this approximation is very good. I mean, these symbols here, the blue symbols are nuclei which are known experimentally to exhibit safe coexistence. As you see, most of them are within those light blue stripes, which are the stripes predicted by the proxy-SU3 symmetry as places where safe coexistence can take place. And actually, this result somehow attracted attention, and it was published in the cover of the journal where it was presented. In the last couple of years, there has been much discussion about the preponderance of triaxial shapes. There is much discussion within the Monte Carlo cell model by Otsuka, Tsunoda, and so on, who argue that the tensor force is very important for producing triaxial shapes, and this can happen over many places over the nuclear chart, and not only in a few places like it was supposed to be up to now. Triaxial projected cell model calculations by Frauendorf and collaborators are also giving a similar example, that you have triaxiality exhibited over large regions of the nuclear chart. Also, there is a study, a recent study, where consistent modeling of many observables was done all over the nuclear chart, and it was found that the average triaxial deformation is at least of the order of 80 degrees, almost everywhere over the nuclear chart, or higher. Within the proxy-SU3, one can have parameter-independent predictions of the places where triaxiality exists. These are very recent results. As you can see, they're still in handwritten form. Actually, high triaxiality are the red and the blue. Low triaxiality are the green and gray. If we isolate in the next figure only the nuclei where high triaxiality, I mean between 15 and 45 degrees is seen, then this is the result. You see that there are the triaxial nuclei predicted within certain regions, which are given here by gray, and these are the regions where oblate irreducible representations can appear either for the protons or the neutrons of the nucleus, which means that you get triaxiality when the protons are prolate and the neutrons are oblate, or vice versa. This is in agreement with what people have done empirically within the interacting boson model a long time ago in the early 80s. So this provides a microscopic justification of what was done in the IBM a long time ago. So this is our most recent result, and we are still working on that. So I will just conclude with this transparency. As you see, people over the years have been saying that everybody who tried to use SU3 in heavy nuclei has been hurt. And okay, our non-modest comment is that everybody else did it in the wrong way. Okay, this is a nasty comment, but it's a joke, but somehow proxy-SU3 is successful enough for predicting many quantities of many nuclei without free parameters and fitting and so on, just from first principles. Thank you.
Thank you, Dennis, for this talk. May I ask, do you have pairing in these calculations? Do you have pairing?
Pairing.
Yes.
Oh, in this, in all these results, I have shown to you, no, we do not have pairing.
Okay.
And this shows up in results which I did not show you today. From this theory, you can have parameter-independent predictions for the collective shape parameters beta and gamma. You can also have predictions for beta. Well, actually, yes, I showed you one figure with that. If you compare these predictions to the experimental values of beta, which you can get from the BU2 from 0 plus to 2 plus within the ground state, then you see that the agreement beyond the middle of the cell is perfect. Before the end of the cell, and especially in the beginning of the cell, it's not good. Especially in the rare earth below 90 neutrons, it is not good. This means that we have to include pairing in that case. Because if you have a few valence protons and few valence neutrons, then the influence of pairing will be larger. If you go beyond the middle of the cell, both in protons and neutrons, you have plenty of protons, plenty of neutrons, plenty of proton-neutron pairs, and then pairing becomes unimportant. So the answer is yes, we should include pairing, especially in the beginning of the cells. This is quite clear by now.
Can you extend this model to even heavier nuclei?
Oh yes, there is no limit. I mean, for actinides and super heavies, we have also produced the necessary irreducible representations mathematically, so they are ready, they are sitting there, they can be used.
Isotopes, not only. I mean isotopes with very heavy nuclei.
Yeah, well, you can go as much as you like, I mean, as far as you like, in the sense that from the mathematical point of view, there are by now codes which can handle those higher cells. And we have calculated the necessary reducible representations. So you can easily calculate beta, gamma, and various other things without any free parameters. We have made comparisons up to the light actinides, where there is also a substantial body of experimental data. Beyond that, we have not tried anything anymore. I mean, for super heavy nuclei, there are some results, so one can make comparisons, but we never tried that. But it is sitting there, one can do that easily. I mean, from a mathematical point of view, we have produced the necessary numbers, so one can do the comparison very easily.
You don't mean neutron stars, I believe.
Yeah, close to the neutron triplet.
Okay. Oh, okay. Not neutron stars, I mean. This is different. Okay, further questions? I don't see them. Thank Dennis again. So, next speaker is Unal Yildirir, and he will speak about single folding potential populations in 141 ER, presumably. The other window. Or you have. Do you find it here?
Good morning. I am Unal Yildirir. Yes, okay. Good morning. I am Unal Yildirir from Antalya in Turkey. Single folding potential calculations in proxy-SU 141. The ground state properties of nuclei, especially nuclear density, are generally calculated using Scairmy and Goni forces. The nuclear densities of proxy-SU 141 calculated by three Hartree-Fock methods. For Hartree-Fock methods, the option nuclear densities for PR 141 have been compared with each other. The Hartree-Fock codes are a useful tool to describe the ground states properties of the spherical nuclei. Spherical HF codes have been used for several years and are developed by deriving gradient interactions. In HF approach, equations are solved using an iteration, namely harmonic oscillator or Wood-Saxon wave functions are recommended for wave function. The density rho is generated based on these wave functions. Then iterations are made between the intensity and U energy potential for phi wave function. The Scairmy force is the effective force for each F calculation. In this way, quantities which are very important and can be measured experimentally, such as core, radius, density distribution, and surface thickness can be calculated. Scairmy forces are the best phenomenological force used to describe the ground states of nucleus. Scairmy interactions, including the interaction of three objects with two-body interactions, is defined as this. The first term defines two objects, and the second term defines interaction of the bodies. Short-range two-body interaction is given as the equation, this. And Scairmy, HFB, many properties of nuclei can be described in terms of a model comprised of independent particles moving in an average potential. The space dependence of this potential should closely follow the matter distribution from the Scairmy HF method. Using this model for independent particles as a single particle potential can be derived from the two-body interactions. This is done using a variational principle with Slater determinations. For example, harmonic oscillator or Wood-Saxon have functions. As real wave functions, the most general product wave functions in the Scairmy HFB theory consist of independently moving quasi-particles. Such wave functions are determined using a variational principle, and they take into account as many correlations as possible while remaining in static single particle picture. Goni forces, another self-computable field method, is a Goni model using Goni interactions. Goni force is the interaction of two non-divergent of particles, and its parameters are arranged according to experimental data. Nuclear densities, the neutron and proton densities are given by this equation, where Q indicates neutron or proton density, and W beta denotes the occupation probability of the state beta. For the SHF method, PCB represents the single particle wave function of the state beta. Alternatively, for the HFBS method, PCB represents the quasi-particle wave function of the quasi-particle state beta. Using either method, the RMS radio of neutron and proton density can be evaluated using upper equation and the following formula. SkyMap parameters are listed in the table, which are used in the calculations. And charge radius of the nuclei are compared with experimental data. Also, proton density and neutron density graphics. These graphics calculated by 4 different methods. It can be seen that all methods give similar results. Single folding potential. Elastic scattering data can be analyzed using the HF code, in which the calculated values replace the phenomenological true potential. Double folding potential is used in the nucleus-nucleus interaction. In the equation, the terms rho 1 and rho 2 represent the nucleon densities of 2 colliding nuclei. R indicates the distance between the centers of mass of the nuclei. The relative vector S indicates the distance between the interacting nucleon pair, while N is the normalization factor, is gives the effective nucleon-nucleon interactions. The nucleon-nucleus reaction is called the standard single-fold optical model. Single folding potential and is expressed is given below equations. The V interaction potential depends on the density, because the folding integral is taken depending on the density of both interacting nuclei or nucleon. The nucleon-nucleus interaction potential includes effects that depend only on the density of a single nucleus. Mathematical code listing for calculation of PR 141 elastic interactive reaction for given energies. And also the table gives us theoretical and our work's results. These potential values used in the Thales code to calculate angular distribution cross-section for different energy is 1.20 MeV and 170 MeV. For 1.90 MeV, so 14 MeV potential energy. And thank you for listening to me. Okay, finish.
Questions, comments, please?
Sorry, do you want to answer the questions?
There is a question there.
In neutral
answer. Yes. Okay.
Then there is a question there.
Okay.
in neutral current neutrino nucleus scattering, the neutron form factor is necessary to be reliably calculated. Have you tried such calculations? Or can the model provide reliable calculations for the neutron form factor, the neutron density?
Yes. Professor Dr. Ismail Aksarpin.
Sorry, we didn't take the neutron densities or so on in our calculations because our models all include all of them.
The you calculated only the proton densities.
No, also neutron densities, and our models take into account all neutron form factor or other properties.
Okay, then the second step is to apply and provide some events of this reaction,
Yeah.
which is very important.
In fact, in all lanthanides nuclei, these potential calculations have been realized. This is part of my PhD student's thesis. And I think if we expand these works to all energy and to all nuclei, then I think we will have some our potential values for all application neutron elastic reaction.
There are two information for the comparison of these neutron form factors. One from astrophysics point of view and the other from experiments which are going to be done in Osaka and Japan in general. Thank you.
Thank you.